Today, I have the great honor of introducing you to Madeleine Lowery. And Madeleine is professor in the School of Electrical and Electronic Engineering and the head of Biomedical Engineering in UCD. And I will be speaking to her about neuromuscular systems and neural engineering. You are very welcome, Madeleine. It's great to have you on here.
Thanks very much, Patricia. It's a pleasure.
Great. So first question for you today, Madeleine, is your work is so interdisciplinary and it's so real world focused. And I'm wondering if you could give the audience an overview of what you do and how you got here.
Sure. So we work in my research group, we work in the area of neuromuscular systems and neural engineering. So I'm in the School of Electrical and Electronic Engineering, as you mentioned. So my background is in electronic engineering, but my research is in the area of biomedical engineering and specifically around the nervous system and the neuromuscular system. So we use engineering methods. So methods like developing computational models, using advanced signal processing methods, using experimental methods to record signals from the body, in order to understand how the nervous system controls muscle, how it controls movement, and how that changes, for example, as we age or with different diseases. And ultimately, what we want to be able to do is try to improve motor function, so improve movement for people. And we're also interested then in the development of technologies that can interface with the nervous system in order to do that. So, for example, using electrical stimulation to restore movement or to be able to improve patient symptoms in different conditions.
So, Madeleine, my next question for you is around your work, and just maybe tell us a little bit about more your research into how the nervous system controls muscle in healthy and disease states.
Okay, so we can record when muscle contracts, it generates electrical signals. So it's very like the heart. We're familiar with ECG signals that you can record from the heart. And similarly, you can record EEG signals from the brain. So when muscle contracts, it generates electrical signals that we can pick up either with sensors implanted within the muscle or placed on the skin surface. And those signals, known as EMG signals, contain information about the state of the muscle and also about the nerves that control it. So we can use signal processing methods, so engineering methods, to extract out that information and understand how individual nerves control the muscle fibers that allow us to do the movements and interact with our environment. So we use a combination then of experimental methods with signal processing methods to get a sort of a window into the nervous system.
Amazing, thank you. And your work involves deep brain stimulation, such as in neurodegenerative disorders. So maybe, like Parkinson's disease, maybe you could tell us a little bit about that, please.
Sure. So one of the things that we're interested in is understanding how deep brain stimulation works. So deep brain stimulation is a therapy that's been around now for about, coming close to 30 years, and it's established as a method for treating the symptoms of Parkinson's disease. So it involves implanting electrodes within the deep structures in the brain, and they deliver very tiny electrical impulses to the brain. And what it does is it changes the firing patterns of the nerves within the surrounding tissue. And we can use engineering methods to build models to understand, first of all, what the change in voltage and current is in the tissue surrounding it and how it affects those activity patterns of those neurons. And we can also then try to understand how that changes the activation patterns of the muscles. So in doing that, what we hope to do is understand how it works, so to get a better understanding of the mechanisms involved, and ultimately to come up with more advanced technologies or better ways of treating patients with, say, implantable stimulators or with deep brain stimulation.
Thank you. And we've already got a lot of questions coming in, but I want to ask one question before we kick off. Is how did you get here, Madeleine? How did you get to this? Where what's your background?
So I was always interested in engineering and medicine. That's where I was torn between the two of them originally. I picked engineering and then I picked electronic engineering because I enjoyed the mathematical aspects of it and the electronics of it. But I also saw a path through it into biomedical engineering. So I did a PhD in biomedical engineering after I did my undergraduate degree. And then I went to the States, to Northwestern University and the Rehabilitation Institute of Chicago. And I worked there for several years. And I was working in upper limb prosthetics and targeted muscle reinnervation there before I came back to UCD then and continued on our work looking at muscle function and modeling and then electrical stimulation and into deep brain stimulation.
So deep brain stimulation, we've questions coming in around that. So here's a question for you. How are brain computer interfaces helping to restore motor function?
Okay.
And what challenges still need solving?
Great. It's a great question and a huge area. So the idea is for people maybe with very high level spinal cord injury, or people with maybe brainstem stroke, particular strokes that would mean that they can no longer interact with their environment. What we want to do is develop brain-machine interfaces that could take signals from the brain and interpret those and allow people maybe either to speak, through a system, or to interact with their environment, to move a cursor, to move a robotic arm. And there's a lot of challenges there. So you can use either implantable sensors, which are implanted on the cortex, they're fully implantable, or you could use sensors that are non-invasive, something like EEG signals. We have some work looking at implantable sensors where we're developing new types of electrodes that will integrate better with the brain tissue. And ultimately, we'd like to use those for speech prostheses. But there's a lot of challenges around the long-term stability of these electrodes. So even though the technology now has been evolving over the last 20 years or so, these electrodes have been implanted in less than 150 people worldwide. So one of the problems is that how do you interpret the data? How do you extract the data? And also around the longevity of the electrodes themselves. How do you maintain the integrity of them so they continue to record high quality signals for long periods of time? But there's a huge amount of work being done in that area worldwide.
That's incredible, Madeleine. And in terms of the data, there must be a huge amount of data generated.
There's vast amounts of data generated, and that poses challenges as well in terms of how you interpret it, how you manage that data, and then how you extract, the information from it. But one very important part of that as well is the human in the loop. So, we talk a lot about machine learning, and the information is extracted from it, and then we can use machine learning algorithms to learn. But the human in that loop as well is critically important, because they learn how to sort of tailor their signals, or how to work with that machine in order to, close that loop and to get it to do what they need it to do.
And with diseases like Parkinson's and the muscle tremor associated with these diseases, is there anything you can do for people with this deep brain stimulation with the devices you've created?
Well, there's a huge amount. So the devices are manufactured by the large, medical device companies. And what we're doing is we work to try to understand better how it works. And it's very, very effective in treating the symptoms of Parkinson's disease in particular. So it can improve tremors and improve bradykinesia, slowness of movement, and akinesia by about 60, 70, 80% in studies. We still don't fully understand exactly how it works. And on top of that, there's a huge range of stimulation parameters that you can choose for any individual. So you can change the amplitude of the current that you're delivering. You can change how long it's on for, the duration of it, and how frequently those pulses are delivered. And in doing so, then you can try to tailor it so that you can get better control of the symptoms for that patient and avoid any side effects as well. But it's a vast parameter space, and difficult for clinicians to find that optimal set of parameters for a particular person. So we're working to develop closed loop algorithms that could automatically send signals from the body, interpret, the patient's symptoms and side effects, and then adjust the stimulation parameters automatically. And that's ultimately what we'd like to be able to do.
And would you work something like this in conjunction with drugs like levodopa or drugs similar to that? How would that work?
So most patients with DBS still take levodopa, mostly for their non-motor symptoms. But one of the advantages of a sort of a closed loop system, like we're trying to, develop algorithms for, is that as patients' symptoms might fluctuate through the day, for example, as they take their drugs, as they take levodopa, the DBS would respond to that. So it would sense that there's a change in patients' symptoms or their side effects, and it would be able to adjust the stimulation in order to titrate it. To provide just the right amount of stimulation for them at that time. So it would allow it to automatically to adjust to changes over the course of the day, or long-term changes over months or potentially years.
And there's another question in the chat as well for you from Keith Murphy. So will superficial or cortical brain stimulation be able to replace some aspects of DBS to make it more accessible for clinical use?
The simple answer is we don't know, but it would be great if it could. The results are quite promising in some ways, because there has been studies using optogenetics, which is a specialized technique that lets people kind of identify pathways involved. And there's very strong evidence that by stimulating some of those cortical neurons, or the axons that come down from them, that's beneficial in Parkinsonian animals and in humans as well. So that would bode well for it, or, promise, it would suggest that it could be a very promising path. But we need to work out exactly where to stimulate and then how much stimulation to deliver.
Amazing. Exactly, and it's almost you have to decide on how that's delivered, even of course the course of 24 hours. I'm sure there's almost a diurnal rhythm associated with this. Would I be correct?
There is, and there's some interesting work as well by colleagues in Oxford where they're looking at changes, during the night. So even at a simple level, you could look at changes during sleep. So even if you could adapt the stimulation just based on people's sleep patterns or their, rhythms during the day, you should be able to get a more refined type of stimulation as well that would, again, provide better control of patient symptoms and side effects.
And another question for you in the chat is, thank you first, Madeleine. Have you or your team done any work in fascia or piezoelectric properties?
Of the brain tissue, we've done work on the electrical properties of brain tissue, and that probably would be the closest to what we have. So Judith Evers, who was with my group, she's a colleague in the vet school. So Judith is looking at what the electrical properties, the conductivity and the permittivity of the tissue in the brain is, because that's really important because it determines how far that electric field spreads. When you place the electrodes in, it determines what the currents are around it. And it depends, it's different in different directions. It's different along the white matter tracks than it is in the grey matter.
And just something you said about how often this is used across the world. So you maybe said it's in, the DBS implanted about 150 patients. Is this in Ireland?
Oh yeah, so DBS has been the brain-machine interfaces which allow people to communicate with their environment. Those sort of neuroprostheses are only in about 150 people. But deep brain stimulation as a therapy is close to probably it's 300,000 people or more worldwide. So it's a very, at this point, it's a well-established therapy. So since 2021, it has been available in Ireland. Prior to that, all the Irish patients who needed it needed to go to the UK or to Northern Ireland. But Professor Catherine Moran in Beaumont Hospital is a neurosurgeon there who came back to Ireland, and she has started doing the surgery in Beaumont Hospital. So the devices are placed very carefully. There's a whole series of MRI, preoperative MRI and imaging and planning that goes on. And then the electrode is placed very carefully within a substructure within the brain. And then after the patient recovers, after a couple of weeks, then they come back in to the DBS service, which is led by Professor Richard Walsh in the Mater Hospital, and he will program their DBS stimulator for them.
Okay, and so you're talking a lot about neurodegenerative disorders, but what about rehab? Maybe rehab for people with traumatic brain injury.
Yeah, so we do some work as well in rehab. That's kind of underpinning an awful lot of it. So understanding, what is the best type of rehab that somebody can have. In Parkinson's, there's an example we've been working on we did a study a few years ago it's a therapy called LSVT big therapy. So it's an exercise intervention with a particular type of, it focuses on large exercises. And it has been shown to be effective in patients for some motor symptoms. And we worked with the hospital, with an occupational therapist in the Royal Hospital in Donnybrook to try to quantify the changes in movement and in gait speed in patients undergoing this therapy. So you can, you have everything from sort of exercise interventions, so using sensors maybe to either monitor those exercises or monitor the improvements in movement that you see, or then you have the development of technologies. So developing things like prosthetics, or prosthetics that can have multiple degrees of freedom, so you get more natural movement and can start to look at sensory feedback as well. And then we have colleagues here in engineering working as well on things like rehabilitation robotics for people after maybe brain injury or after spinal cord injury.
And unfortunately, we're running out of time, but just one more question that I want to ask you is around the future. So you've spoken about a lot of incredible technology and incredible innovation and some of the other work that's going on in engineering in UCD. But, the next 10 years, Madeleine, what would you like to see? How would you like to see this change people's lives?
Well, I suppose if we take DBS, what I'd love is if it can, I suppose you can reach a much bigger patient population, to provide benefit to people maybe a little bit earlier on, and a much more tailored intervention. And I think that's probably where the challenges lie. And that's where I think we're looking at sensing and stimulation in combination. And again, say, even if you're developing a rehab therapy as well, that you can sense what's going on with the individual, and that allows you to give a much more personalized approach to that, therapy, that intervention, that type of rehabilitation. So if we can combine, I think, sensing and stimulation, or sensing and interventions like that, then you can close the loop and really provide a much more targeted, more effective treatment and therapy for people.
It's so exciting, Madeleine, but unfortunately, we're completely out of time. And I just wanted to take this opportunity to thank you for the most fascinating discussion today. Thank you so much, Madeleine.
Not at all. Thanks very much, Patricia. Thanks for the opportunity to talk to you.
It's fantastic. And thank you to everyone for joining in. And please do check out our series online, and see you all very soon on our next UCD HIT series. Thank you so much. Have a great day, everyone.